So it's my pleasure again to introduce Henrik Johansson from, well, no, wait, Uppsala, sorry. Yeah. Scattering amplitudes and for Kerr black holes and higher spin symmetry.
All right, thank you. Yeah, it's a pleasure to be in Southampton for the first time. It's really an honor to be invited here. So thank the organizers and the chairman. So I will talk about something related to black holes and amplitudes, and maybe this is like the novel perspective. I'm going to look at very simple amplitudes, but I'm going to include spin, which makes it very complicated. But let me start with some very mild motivation. So you all know that studying binary black hole systems is very important, and people have done it in several ways in the PN and the PM expansion. We heard it from Pierre's talk, I think it was maybe Monday. Another thing that's very important to include for astrophysical black holes is the dependence on spin. And so in principle, there's a few different methods to use. None of them are very perfect in the terms of efficiency. They're quite complicated, but let me just mention them here. So one of them is called black hole perturbation theory, and that's basically just going back to GR, starting from a Kerr background and introducing perturbations on that background. So that's the sort of the truth. Then there are some effective approaches, which are worldline EFTs. Recently, people have been studying quantum scattering amplitudes and writing down some guesses for what they could be when you have spin, and then they have been able to show that they actually match black holes. And then lastly, what I'm going to talk about here today is you can also think of black holes by quantizing the spin, so just treating it fully quantum mechanically, and then you have to use the language of higher spin QFTs. All right, so specifically the process that I'm interested in is not 2-to-2 scattering of two black holes, but I'm just interested in one black hole where we send in a beam of gravitons, and then we look what comes out. So that's basically the Compton process. And there's a few rules or a few, it's a few statements here that I want to say. So first of all, I'm going to think of the asymptotic states as being eternal black holes, meaning that they're only characterized by mass, spin, and charge. And most people are not interested in the charge case because that's not relevant astrophysically. Now, in principle, there should be finite size effects, but I'm going to think of them as being loop effects because they should be proportional to G, and G comes together in the Schwarzschild radius, so that's the finite size. So once you include loops, hopefully they should come. So if you worry about horizon effects, tidal effects, quasi-normal modes, etc., there should be loop effects, so I'm not going to talk about it here today. So what I'm going to do is going to do tree level, and tree level has a weird quirk that in order for it to be defined, you have to actually take GM to be smaller than S over M, so this actually means super extremal Kerr. You might worry about that, you know, how do you, is that physically relevant, but when we work with amplitudes, we're very happy to analytically continue, so just pretend that everything is analytically continued. So essentially, I'm going to assume that I'm actually scattering point particles. And hopefully it's going to work out, and the short story is that it will work out. And basically, we'll try to sort of bootstrap this Compton amplitude to figure out what the black hole dynamics is. And from that, we can then deduce some kind of EFT. The EFT is roughly going to look like the schematic one that I wrote here. It's going to be some higher spin field. It's going to be a kinetic term. There's going to be corrections which are in some series expansion, and the Riemann tensor, or here's the Riemann tensor. There's also derivatives which I've suppressed. But essentially, the way you can think of it is that there's a single Riemann that's basically sensitive to the one graviton. If you have two Riemanns, they're sensitive to two gravitons. So that's specifically what I'm interested in here, two Riemanns. All right, so that was the motivation. Then the rest of the talk will be, I will talk about some kind of known stuff, which is the Kani-Hammett-Wang higher spin amplitudes, which are 3-point amplitudes. I will also talk about, how that's related to something called Janice-Newman shift and so on. But then I will get to the Compton scattering and say that there are some problems in finding the correct Compton amplitudes. There's some issues that appear if you just do it naively. And then I'm going to try to discuss our methods for resolving it. So we have two methods which work pretty well. One of them is to think of it as a higher spin gauge symmetry and introduce an EFT which has a lot of higher spin fields. The other way to do it is completely the opposite, which is basically we reduce to something which has the minimal degrees of freedoms that are needed for a higher spin particle, and that's by going to chiral fields. And I will talk about that as well, and they nicely complement each other. All right, so let me start talking about the 3-point amplitude before I get to Compton. So there's some very nice work from 2017 by Hamed, Huang, and Huang, where they just tried to write down the most general higher spin amplitudes using massive spinor helicity, which they also introduced in that paper. And they came to the conclusion that these amplitudes here are very nice. They call it minimal amplitudes. The minimal has nothing to do with, the minimal interaction, but they're minimal in some sense in this language. And they look very chiral. The theory is actually not chiral, but this is the plus helicity graviton scattering, and this is the minus helicity graviton for any spin, integer or half integer spin. Then at the same year, actually, there was another amplitude computed from the stress energy tensor of a Kerr black hole. Here I just wrote down the stress energy tensor, but you can saturate it with two polarizations, and you basically have your amplitude there. And it was actually shown in some paper that these two actually are equivalent in a classical limit. I will come back to that later on. Let me also mention that there is a third perspective of thinking of spin in the world line formulation, and then you have to do what's called a spin multiple expansion. And I'm not going to explain it here. You can go to the original references.
Can I ask, why the image momentum flash has a delta function?
Why does it have one? Oops, sorry. Well, there's a condition that, let's see. It's going to take too long to explain it, but let's talk it afterwards, yeah. But essentially, that is actually one of the kinematic constraints. I'll explain it later, yeah. Let me also explain some notation here. Maybe this gets a bit technical, but let me try to do it in a way that it sounds cool. So we're going to think about the spin operator in quantum mechanics, and we're going to map it to our 3-point amplitude. Basically use it as one of our variables. And the way we can do that is we introduce some SU2 wave function, which also parameterizes the tree-sphere, basically if you use corrective coordinates. And that's actually just telling us how much up and how much down our spin wave function, how much pointing up and down. And using that, we can actually parameterize the classical spin here. So this is a spin vector, classical spin vector, and it's parameterized in the spin S representation. And to do that, it's proportional to S, so that's basically the magnitude. There's some dependence on the wave function to some arbitrary, some power 2S, and there's some spinor helicity expression. This is Pauli matrices. The property of this is that it's transverse. It's also the expectation value of the operator. So this is the expectation value of the operator. If I actually want to know operator, I can just take derivative with respect to the Z. And then if I extract the operator, I can check that it satisfies the proper quantum mechanical properties. So it has the commutation relation correct. It has the quantum mechanical square correct. So using this, I can actually try to now match the spin helicity expression that I showed on the previous slide with the spin operator or spin classical spin. And in order to do that, let me introduce a little bit more notation. So in the massive spin helicity notation that Hamed, Huang, and Han introduced, they essentially introduced this spinors, which labels a particle I. It has a little group index A, and then has the suppressed Lorentz indices. This spinors basically define a map from the Lorentz group to the little group. You don't need to know more than that, but they're very convenient notations for describing this 3-point amplitude. So I didn't explain what that 1, 2 to the power 2s is, but in this notation, it's just two Weil spinors contracted. They're also contracted with the SU2 wave function. And basically what it does is it turns this into a polynomial in my wave function variables. So here's a very simple example. If I want to look at a massive polarization vector, I can use this massive spinnericity, and that then, if I just expand it out, I'm going to get decomposition into the m quantum numbers. I'm going to get the minus helicity, zero helicity, and plus helicity of the massive spin 1 particle. It also has a feature that is actually a null vector, so I can actually construct an arbitrary higher spin polarization this way, and it will automatically be symmetric, transverse, and traceless, because these are actually null vectors. All right, that's the notation. So now I want to take this 3-point amplitude, which is written on this form, and I want to massage it into the spin vector or spin operator. So one thing I need to do is actually need to relate the variables on the outgoing leg to the variables on the ingoing leg. And I can actually do that with a boost. I'm not going to explain too much, but this is actually just a boost, change of variable, essentially. And if you do that carefully, you will notice that this expression is actually formally equivalent to this exponentiated operator, spin operator, which I can write that. This is a finite sum here, but this is a finite sum because it's a finite representation. If you just extend the range of S, then eventually it will become a full exponential, and so this equation is actually exact even for finite S because of the finiteness of representation. Then you get this very nice formula. So it turns out that the prefactor, which I didn't write here, that actually is the 3-point Schwarzschild amplitude as far as we know. It matches all the GR calculations, so that's just the same as a minimally coupled scalar. And to get the Kerr, all you need to do is you need to add this exponentiated factor, and this is also related to the Newman-Janis shift, except here I actually have not yet taken a classical limit. So that's very interesting. There's also something called a root Kerr gauge theory amplitude, which I haven't really introduced, but I will actually come back to it later on. And that actually has the same relation to the Coulomb 3-point amplitude, and this is just a minimally coupled charge scalar. So it's very interesting that there's these two formulas which are very similar. And if you wonder what A is here, A is just what's known as the ring radius. Well, it's typically a vector or a scalar, but here it's actually an operator because I just define it to be the spin over n. All right, so that's a 3-point story. Sorry if I went a bit quick. The next thing I want to discuss is the Compton amplitude. Starting from Akane-Hamada-Huang 3-point amplitude, you can actually compute 4-point amplitudes, and you get this very nice simple formula, which is very reminiscent of the 3-point. It's also just on power to the 2s. Unfortunately, it has a problem. The problem is that there is, for dimensional reasons, you need to put something in the denominator. You would like that thing in the denominator to be a mass, but it turns out to be this spinorial expression here. You see, when S goes beyond 2, this ends up in the denominator. And this actually is not a physical, this has some poles. This is not a physical singularity, there's a spurious singularity. So it's something that shouldn't be in the amplitude. Now you can say, well, that's fine, let me just subtract it out, and you can do that, but the subtraction has some ambiguity, and these are the contact terms of this amplitude. So these are not well defined from this procedure. So they need to be calculated in some other way, because those contact terms are relevant for 2-to-2 scattering. So for example, here, when you do 2-to-2 scattering, you will have a Compton amplitude here in this vertex here, and so you need to know how it interacts. All right, I should also say that there's two different Compton amplitudes. There is the minus plus helicity amplitude and the plus plus. And in fact, the plus plus is actually much simpler, and this does not have the spurious poles problem. I think it wasn't actually written down in that paper, it was written down later on, but it's essentially trivial to compute from the 3-point Akane-Hamada-Huang amplitudes. Here I also have the similar problem in the root Kerr gauge theory, but maybe I should just skip this because I'm running out of time. So let me quickly say what are what are the theories that gives these amplitudes? So for example, at low spin, we can just think, are there some theories that we already know that gives these amplitudes? And the answer is yes. Let me just skip a bit. So the answer is yes. Like if you just look at the minimally coupled Majorana fermion and compute the Compton amplitude, it exactly matches that formula. Likewise, if I do a minimally coupled Proca massive spin 1, it exactly matches that. Likewise, if I do a Rita swinger, it exactly matches that formula. For spin 2, it's a bit trickier, but you can show that it's actually a Kaluza-Klein graviton that matches that formula. Then, if you go beyond spin 2, it's not clear what those theories should be. It doesn't look familiar to anything that we know of. And as I said, there's also this toy model, the root Kerr, which is closely related at 3 point to the Kerr, and you can do the same analysis there. Is there some gauge theory that matches those 3 point amplitudes, which looks almost the same as the Kerr? And yeah, for spin 1/2, it's direct. It's direct because it has to be charged. For spin 1, it's actually not a Proca, but it's actually a W boson. You need to include the non-minimal interactions of the W boson, otherwise it doesn't work. And likewise, when you do spin 3/2, it's actually not just a Reuter-Swinger field. It's a Reuter-Swinger field plus the non-minimal interactions that you need in order to promote it to a gravitino, actually. So this is actually a gravitino that couples to the graviphoton, and you have thrown away the graviton and so on. But essentially, the interactions are the same as you would find in a spontaneously broken n=2 supergravity. So I think from this table we can take some lessons, and the lessons are that this series are very nice series. They all have something to do with some spontaneous symmetry breaking, the W boson, the massive gravitino, and massive Kaluza-Klein graviton. So that's the lesson that we want to take home, and we want to use it to develop higher spin theories. So higher spin theories have been studied a long time, and there's a lot of confusion surrounding them, especially in the early literature. Most people studied massless theories in ADS, but here I'm going to just study massive theories in flat space. Let me actually skip here. So, let me discuss this. As I said, one thing that's very interesting about this series that we already observed that matches the Compton amplitude and matches the 3 point amplitude is that they have something that looks like spontaneous symmetry breaking, but it's a broken version of it. They also have a well-defined massive limit. So if you actually just take the massive limit, then we get the unbroken series. So we get the spin 1, Yang-Mills in the gauge theory case, and we get basically a graviton amplitude back for the spin 2 gravity. And so we take this lesson that there is something about this theories which has to do with spontaneous symmetry breaking, and then we look up in a paper from I think from the 90s, but Parati et al. There's some follow-up papers, and he also studies the problem of tree-level unitarity constraint, which is essentially trying to find a UV completion of higher spin theories, and he comes to the conclusion that in order for that to exist, some version of the higher spin theories where they're well behaved, you have tree-level unitarity, the amplitude doesn't grow too fast, you need to impose a constraint on the longitudinal modes, and essentially this means that you impose a current constraint, which is very similar to a Ward identity, but instead of saying that the right-hand side should be 0, you say that it should be order m. And this is actually highly non-trivial. It looks almost trivial, but it's highly non-trivial because typically your interactions will have loss of powers of 1 over m. So the fact that when you saturate the momentum of the current into the current, the fact that all the 1 over m to some very high power goes away is highly non-trivial. All right, so this is one of the constraints we're going to use, but we're also going to use massive higher spin gauge variance. These two constraints sometimes seem very similar, but they're not exactly the same thing. So we're going to use both. So here's a very simple spin 2 example in gauge theory. So let's just do this because it's simpler than doing spin 3 in gravity. So for spin 2, I'm going to introduce 2 Stuckelberg field. I'm going to introduce a spin 1 Stuckelberg field and a scalar Stuckelberg field. And then I'm going to demand that there are some linearized version of a massive higher spin gauge transformation. Obviously, if I set the masses to 0, you see that's just ordinary gauge transformation. And you can figure out that, once you include a mass, you also need to include corrections. Xi here is a gauge parameter. There's a scalar gauge parameter and a vector gauge parameters. So imposing these gauge transformations, make sure that the degrees of freedom are correct, that we only have spin 2, we have nothing else. Also, typically, we know that when we impose this on, for example, spin 1 theory, we know that this actually enforces the fact that this is a spontaneously broken theory, and therefore, when you take the mass to 0, this should be better than naively expected. All right, let me skip this. This is basically just how we do our ansatz. We build up an ansatz. For the vertices, we do it very brute force, order by order, and then we impose some gauge transformation using some differential operators, because it's going to be simpler when we go to arbitrary spin. And then we try to find the amplitude after having constrained that. And it turns out that gauge invariance by itself doesn't quite fix the amplitude uniquely, at least in this gauge theory. So we also add the current constraint, which I just discussed, and that actually fixes it uniquely for this spin 2 example. But let's do it in general. So let's do it for arbitrary spin. So I'm going to introduce a tower of higher spin states that goes all the way from 0 to spin s. Spin s is our physical state, and all the other ones are Zuckerberg fields. And I'm going to use this framework of Sinyovev from 2001. So you assume that the fields are double traceless, meaning that you can take one trace, but when you take the second trace, it goes to 0. Then we have gauge parameters, which we're going to assume just being traceless. Then it turns out you can write the gauge transformation very cleanly for arbitrary spin, this three-term expression. Alpha and beta here are just some numbers, depending on the spin of the top particle and all the lower ones. You can write up a minimal Lagrangian that looks like this. We have actually split it into the Feynman gauge part and the gauge fixing part. Turns out that you can nicely split it into these two parts. And then you can start introducing non-minimal interactions. It turns out once you introduce once you start introducing just minimal interaction, that breaks gauge invariance, even though the free theory has gauge invariance. So you have to also then start adding non-minimal interactions to restore the gauge symmetry, the massive gauge symmetry. And again, we do that by ordered entities. So here I just written down some operator which acts on the polarizations of my vertices. All right, so there's ordered entities that I'm going to impose as the current constraint. Then we also impose some power counting, because if you don't do power counting, you can basically write down anything you want. So we do impose power counting constraint. Then also in the gauge theory case, we do gauge theory and gravity at the same time, because we learn one thing from the other and we import it into the other. And so what we learned is that we can also impose the fact that these fields only have near diagonal interactions, meaning that if you have a 3-point amplitude, you would only have interactions which differ at most by spin, which is actually given by the helicity or the absolute value of the helicity of the force carrier. So that's 1 or 2, depending if it's a gauge theory or gravity. So we can impose that. For the gauge theory, we need it. For the gravitational theory, we don't need it, but it turns out that all the interactions are compatible with that, so that's one constraint. And once we do that, we actually get unique Kerr and root Kerr 3-point amplitudes as far as we have checked. And so the pattern looks very promising. We haven't proved it, but we checked that they are unique. And then once you have 3-point under control, we can start doing 4-point. So here I show the propagator in Feynman gauge. That's of course you need when you do 4-point, and it's actually very clean. It's very clean. It's actually it's actually a generating series which you can expand in epsilon here. When you expand it, you're just going to get the spin 1 Feynman gauge. You're going to get the spin 2 the Donder gauge. To any spin, you're going to get the harmonic gauge or the Feynman gauge. All right, and then we can do some computation, and here's a 4-point example for the gauge theory that we did. Again, of course, you're going to have some ambiguities, which is basically you haven't yet introduced quartic interactions. So the quartic interaction is sitting here. One thing to note is that some very interesting polynomials showing up. Well, maybe it's not so interesting. This is just a geometric series. But there are this polynomial, so they will actually generalize. If I have maybe 2 more minutes, I'm going to show you the generalization of this polynomial. Okay, yeah. I think I started late. Yeah. All right. So in parallel to doing higher spin gauge invariance for non-chiral fields, we also realized that the amplitudes that we get looks very chiral. And so maybe we should actually use a chiral formulation. So instead of using the Lorentz representation s, s, we go to 2s, 0. That, of course, widely breaks parity invariance, but we're going to then impose that parity invariance is actually restored at the end of the day. So this was actually done in a paper by Shiro and Skvortsov, and they were actually using some results from Chalmers and Siegel, which are quite old. But here's actually how the minimal Lagrangian look like, and it's actually much more simple now. So now you have exactly the right degrees of freedom, because once you go to this frame, there's actually no redundant degrees of freedom. And you can actually write up like an all-plus amplitude, which is extremely simple. It's just this 1-2 factor times the scalar amplitude. So it's exactly the same as the AHH amplitudes. You can also do W boson and standard model, which I wrote here, so it looks very non-local. But then, okay, then we need to add non-minimal interactions to restore parity. So that I did here for the gauge theory. This is the non-minimal interactions. Again, this is a chiral formulation. This is basically d slash, but we didn't want to slash it. You can also do it in the gravity theory. It looks like this. So you see there's actually arbitrary number of derivatives depending on which spin you are. So if you're at spin, the sum goes from 0 to spin 2s minus 2, so you get higher and higher powers. Interactions, again, behave actually as a geometric series, and that's actually related to the types of functions that we find in the amplitude when we compute. So as I said, we already found this function, which looks like a geometric series, or a geometric sum. So geometric sum, I can just think of as having a lattice where I assign a variable to each lattice to some power, and then a sum over it. That's a geometric sum. I can generalize that to 2 dimension, then I get this generalized geometric sum. I don't know exactly what it's called. If you do that in arbitrary generality, you get this complete homogeneous symmetric polynomials. It turns out that amplitude is a function of those using these kinematic variables here, or spin variables. And let me just jump to the answer then. Yes. So this is actually our Compton amplitude for the quantum case, and it's very complicated, so I'm not going to explain it. Let me show you the classical result. This is the classical result. It depends on some variables. It depends on some entire functions, which I had in the previous slide. It depends on some variables, 4 variables, which are spin dependent. But it's an all orders result, in all orders in spin. And interestingly, it actually matches explicit calculations from black hole perturbation theory. It matches up to spin to the 7, where we have to ignore something which are called polygamma terms, which have to do with the near zone effects. We suspect there are loop corrections, but there's some debate in the literature whether there are loop corrections or not. But anyhow, let me end there. Thank you.
I have 2 related ones.
Yep.
So this result here is for Einstein gravity?
Yeah,
Yes.
of course, yeah.
And the related question is, do you have a general counting of how many amplitudes there are, like even for the 3-point functions? And for instance, Maxwell and spin S should be 2s plus 1. Do you have this counting?
So 3-point, if you stick to finite spin, the number of amplitudes just grows linearly with spin, right? So roughly, if you're at spin 10, there's basically 10 different operators. It's a little bit less. I think it's 10 minus 1 sorry, it's spin, it's 2s minus 1, I think. That's the precise counting. Yeah. 2s minus 1. That's the different quantum amplitudes you can write down. But you're asking about when I take the continuum limit of spin?
No, just with the spin, but we have different situations. You can have spin S1, S2. You have many different 3-point functions. Is there a general classification?
Well, I think you have to fix the spin to some value, and then it's exactly 2s minus 1 different amplitudes you can write down. And then if you wanna interpolate between different spin, of course, then you can do it in a different way. Let's say you wanna take S to infinity limit, you can find some trajectory through this tower of different amplitudes. So that's a bit more complicated, I guess.
Other questions? I might have a quick one. You mentioned the Kluser-Klein graviton.
Yeah.
That specifically, well, is it something more than just a massive graviton? Because more.
Yes, I mean, it's different that it does have, so massive graviton I would just call Fierz-Pauli. Okay. And then if the Fierz-Pauli Lagrangian, and then you add non-minimal interactions to that, then you get the Kaluza-Klein, right? But there's some ambiguity in how you covariantize Fierz-Pauli, and if you do it in some special way, then you actually get the Kaluza-Klein graviton. But if you do it in the standard way, you don't. So, yeah.
Kaluza-Klein as if it was coming from 5 dimensions.
Yeah. It makes sense. It's just the most well-behaved amplitude, so it makes sense that that's the one that shows up. Yeah.
Are there any other questions? Thank you again. Nice talk.